Hi, so my name is Maciej. I work at JetBrains in the Scala plugin team, and that's all I'm going to tell you about myself or my work, because I'm going to talk about Cellular Automata for video games. That is like a form of an artificial intelligence, and that's much more interesting. So let's go. First of all, some theory. What are Cellular Automata? In a way, it's a model to complex processes by breaking them into sets of rules applied again and again over time on data spread over a discrete lattice of cells. And yeah, that's a lot of talk, but the most important parts here are there are sets of rules that are applied over time, and the board, or like our space, is a board of some kind of fields or cells exactly, and we do it like in a loop. So to translate it into programming language, especially Scala, because this is what I'm working on, we have a cell. A cell can be some kind of a case class or a record that has some immutable properties, and that's just one piece of a very big board. Now, we have a board that can be modeled as a map of positions to the cells. Here we have like a simple, like a chessboard with two-dimensional positions, but in fact it can be anything. It can be many-dimensional, it can have some tunnels, teleports, whatever you like. It might not even be like a physical board, it might not have a physical representation, and I'm going to go back to it later. Then we have a concept of neighborhood. A neighborhood of a cell is all the cells that are directly connected to it. And because of that, the cell can take information from it. That's also more important because it means that for everything we do, we only are interested in the data that is in the cell that we are talking about, we are working on, and the cells that are next to it. It's all local. We don't have to know the state of the whole world. We only need to know the state of like a very small piece of the whole world. So the traditional forms of neighborhood are von Neumann's, that is north, south, east, and west, and the Moore, that is all the 8 cells next to our cell. But also, again, as with the board, in the neighborhood can be anything. It can be hexagon, it can be like whatever you want. And then there are rules. Like if you were here for the last hour, you already know the drill. We have a cell. From the cell, we can get the neighborhood, and them together create a new state of the cell, and then together with doing that on all cells on a board, we have a new board, and then we need a loop or some sort of an iterator that will create new boards, one after another, and after another, until we get something that we can call a result. A bit of history. The whole concept comes from John von Neumann, who was a very important person in computer science just after the Second World War, and he came up with this idea that there can be robots that build their own copies, and this way, if we have a very complex problem, then instead of having a very complex robot to solve it, we can have one small robot that will just build its copies of itself and solve the problem by having enough of those robots to solve it. And John von Neumann was inspired by Petri dishes, but he didn't really like put it further. Another person who took over and talked about it more is John Conway, who in the 70s came up with what we call now Cellular Automata. And of course, rules of the universe force me to mention the game of life if I'm talking about Cellular Automata. So quickly, it's also a good, like a very simple example. In game of life, we have a cell that is only have like a bit of information. It can be alive, that is black, or dead, that is white. And we have a two-dimensional board. We have the Moore's neighborhood, so all 8 cells around the cell. And they're also like that if the cell is dead, it's a white cell. And the neighborhood, we have 3 cells that are alive, black. Then in the next iteration, the cell will become alive. If the cell is alive and the neighborhood has 2 or 3 cells that are alive, the cell will stay alive, and otherwise, if there is not enough alive cells in the neighborhood, or if there is too many, then the new iteration of our cell will be dead. But Yeah, okay. We don't have time for Game of Life, really. I wanted to tell you something about like more modern video games. In 2006 or 7, I worked on a game engine called Jupiter X, the most known, I think, video game made with this engine was a first-person shooter Fear. Feir, and they had like a very simple but also giving like a very nice results artificial intelligence engine that allowed for the NPCs in the game to shoot at players from different directions and switch those places. So imagine we have a room like this. We have 6 cells. This is our world. This is our board. We have only 6 cells there, A, B, C, D, E, F. And we have like a wall in the middle of the room, and the player comes into that room. And he doesn't see, or the player doesn't see that there are villains on the other side of the wall. There are 3 villains, and what we want to have is that they should go around to the point, to the B and to the C, and they should shoot at the player. We can model it, like making decisions how they should do it can be done with Cellular Automata. First of all, what is a cell in such a room and in such a world? The cell is this just like a abstract piece of that tells us that in the given area of the room there are villains. The villains can be, there might be more than one. The villains can be tagged or untagged. Tagged meaning that the villain already knows what to do. Untagged meaning that we need to like make a decision for it. Yeah, it has a player or not. And if the given cell can also have a path that the villain can use to go from the place it is to the player. And the rules go like that. If we have a player, then we do nothing. So the cell A, just like we compute what's going on, and we say, okay, we have a player, that's it, we don't do that. Another thing is that we have some cells that are next to the cells that have players. So they have the player in the neighborhood. And these are the cells that are good to shoot at the player from. So in this case, we start to create a path. We say, okay, the cell B. This is the good place to shoot at the player. We set a path that can go from the villain can use to go to that place. And then, if we have a cell like D that is not next to the player, but it is next to a cell that has a path to the player, so the cell B has a path to A, then we get that path, we add our cells, so D, and that's done. And then we have an untagged villains at the cell E, and they are next to a cell that have a path, so we can just randomly choose one of the villains and tell this villain, okay, the decision is you use that path to go to a place where we shoot at the player. And what's funny about it is that this means that we will have one decision, that one of the villains will go to B, the other villain will go to C, the third will stay where it is because both paths are already taken. And then if I am a player and I see that I have one guy here, and they are shooting at me, I'm already like, oh, wow, good artificial intelligence here. Okay, I turn to one of them, shoot that guy, turn to the other, start shooting at that one, but what's happening there? That place, for example, if this is the cell B, is again empty. So we can again take a decision that the third villain, which is not used yet, will take that path, and while I'm shooting at this guy, he will take that place and shoot at me at my back. So wow, that's again like a very interesting, very well created AI, but this is still only those 4 rules and this one small definition of cell. One thing that is maybe also needs mentioning is that the Cellular Automata that is used as an artificial intelligence engine here is not the same as the game state. It's not like I'm doing all that stuff in the same time as the artificial intelligence doing the thinking. It's like something happening in the world, then the update of the whole game state of the whole world is given to the Cellular Automata. The Cellular Automata makes some computations and then gives results to the game state, and that results are, okay, this villain should go here, that villain should go there. But that's not all. That's already fine for first-person shooters or games like that, but we can do better. Second of all, we have also Cellular Automata can be also used for pathfinding, and that's not only for video games, but okay, let's talk in this context. So we have some sort of a board that where are some walls or places where we can go through, and we want to find a path from one star to the other. We use the von Neumann neighborhood, so north, south, east, west, and the way we do it, because yes, of course, there are pathfinding algorithms like A-star that are quite quick, but they are sequential. But the thing with Cellular Automata is that they can be very nicely processed on a grid of many threads of many CPUs. So this way, this algorithm would work like that. This is a distributed search. So every cell keeps the path from the start, from this point to itself. At the end of the whole algorithm, we will just reverse it. And initially, the path is empty everywhere. So every cell on the board will have the path empty. But the start point will have its own, like the path of the start point will be itself. And then, in every iteration of our loop, we go through these rules. If the path is non-empty, so we already established that there is a path to the start point, then we do nothing. If there is no neighbor for the given cell that actually has a path, then we do nothing as well. That's like, so 99% of the cells will just do nothing every turn, at least at the beginning of the whole algorithm. Then the third rule is that if we have that cell in the neighborhood that has a path, so at the beginning it will be only the 4 cells in the neighborhood of the starting point, then we take that point, that path from the starting point, we add itself to the path, and that's the next state of the cell. And by doing that, only by those rules, we eventually spread the whole, like we search through the whole board to the point, to the moment where we find the ending point. And if we are the ending point, then that's it. We can return the path, well, reverse it. And yeah, so we can use it in the literal sense. Like this way, we can take advantage of GPU on the computer, or virtual threads in Java or whatever, and we can use it for very quick and effective pathfinding. But there's one more thing. As I mentioned before, the board doesn't have to be really a physical board. It doesn't have to be the board at which we play. It can be multidimensional, or it can represent something that is not really a space, like a physical space. We can use this abstraction, we can take it to a higher level and use it as a form of decision-making, where one cell, the starting point, is where we are now in the game, and the whole, the state of the world, and the end point is where we want to be. So in this case, in this abstraction, one cell is going to be a possible state of the whole world. Let's say, for example, that we play a strategy game where we are a country that, and there are a few other countries, and we fight with each other. And the country can have like the size of the army, the wealth, and some resources that can be taxed, and we can get wealth from that. So our cell is, our cell will just be the whole possible, like every cell on this abstract board will be one state of the world that is composed of countries that have those properties. Then the neighborhood of that one cell are all the states that can be achieved by one single action. For example, if I raise taxes, then in the next turn, I will have a bit more money, and that's one step, so that's my neighborhood. Then the board, yeah, it's like graph of all possible states that can be connected by these actions. So I have like 2 states somewhere, and by my actions and the actions of others, we can go from this state of the world to that state of the world. And rules in this case are basically the same as in case of pathfinding. So let's say I'm Poland here, and I want to invade France. I'm at the current state. I have little army. I have little wealth. I have some resources, so typical Poland. And then I go and raise taxes, and then I get more wealth, and then I build a bigger army, and then I invade. And this, you can imagine that this is one path in a very big board, and this is what we found what would be the best way to go from our current state to our desired state on this, using pathfinding on this abstract board. Yeah, as I said, this can be used very effectively on GPU using NVIDIA or OpenCL. And just quickly, if you didn't watch the whole thing, Cellular Automata are a great way to model complex dynamic systems in space that can be 2D, 3D, or whatever. You want to build a backend with it. You want to build a graphical user interface. You will also have a hard time making them find a cat on a photo. It's just not that way, not that form of artificial intelligence. But it is useful for logic for video games. It can simulate complex systems. It can predict the behavior of real ones, because like if the video games is sufficiently complex, it starts to become like a simulation of a real world. And it is good for also different kinds of distributed computing. It allows for quick pathfinding, decision making, and a big advantage of it is that we can implement logic in simple steps, so it's easy for us to reason about it and plan it. Thank you. So again, my name is Maciej Gorywoda. You can find me on YouTube, where there is a longer and less chaotic version of this lecture. I'm also on Twitter or X or whatever the name is. Thank you very much.
Thank you for that. We have just a bit of time, so we can accommodate one question if there is any. Yep, there you go.
Hello, thank you for the talk. Now, can I ask you, if we come again to the pathfinding, the last example, no? What I was asking is, in this example, you build the board every step. It is right? You don't start from a pre-built board.
Yes, it would be quite resource heavy to build the whole possible board of all possible states, but I can do it lazily. Like if I start from the current situation and just simulate what can be done in one step and then another.
Okay. Thank you. So please another round of applause, and I guess it's lunchtime.